The next marketing question that we'll like to answer through marketing analytics is around targeting, particularly who is likely to buy. Note that this question is statistically the same as who is likely to respond to a message or an offer. This probability question is the center of marketing science in that it involves understanding choice behavior. The typical technique involved, especially for database direct marketing, is logistic regression. So, logistic regression has a lot of similarities to ordinary regression. They both have dependent variable, they both have independent variables, they are both single equations, and they both have diagnostics around the impact of independent variable on the dependent variable as well as fit diagnostics. But their differences are also many. Logistic regression has a dependent variable that takes on only two as opposed to continuous values of 0 and 1, that is, it's binary. Logistic regression does not use the criteria of minimizing the sum of the squared errors, which is also ordinarily square or OLS, to calculate the coefficients, but rather maximum likelihood via a grid search. The interpretation of the coefficients is different. Odds ratios are typically used, and fit is not about predicted versus an actual dependent variable. As a slight detail, another important difference between logistic regression and ordinary regression is that logistic regression actually models the logit rather than the independent variable. A logit is the log of the event by 1 minus the event, that is, log of the odds of the event occurring. Recall that ordinary regression models the dependent variable itself. By the way, yes, there is a technique that can model greater than two values, but not continuous. That is, the dependent variable might have 3 or 4 or 5, etc. values. This technique is called multinomial logit. Discriminant analysis will do this as well, but we will not cover it now. All of this above means that the output of logistic regression is probability between 0% and 100%, whereas the output of ordinary regression is an estimated value to fit the actual dependent variable. Now let's look at some data and run a model, because that's where all the fun is. Now Scott was very impressed with what he did on demand modeling, calls Scott into office. Scott, we need to better target those likely to buy our products. We send out millions of catalogs based on magazine subscriber lists, but the response rate is too small. What we can do is make our mailing array better. Scott thinks for a minute. The response rate was too small. Response rate is the rate of response, which is the number of those that responded divided by the total number that got the communication. It's an overall metric of success. We want to target those likely to purchase based on a collection of characteristics. We have both customers and non-customers in our database. From the subscribers list we have been mailing, so we could model the probability to respond based on clone or lookalike modeling. What does that mean? The boss asks. I'll have to dig into it a bit more, but I know we can develop a regression type model that scores the database with different probabilities to purchase for each name. We can sort the database by probability to purchase and only mail as deep as ROI limits. So now we get into the list of customers that purchased and those that did not purchase. Scott has data on which campaigns they each received, as well as some demographics. The objective is to figure out which of the non-purchasers look like those that did not purchase and re-email them. So which of the non-purchasers look like those that did purchase, and re-email them, perhaps with the same campaign, or design another campaign. The end result will be to score the database with probability to purchase in order to understand what statistically works and strategize what to do next time. This is the cornerstone of direct marketing. Using dataset, you can run props logistics descending in SAS. These coefficients are not interpreted the same way as in ordinary regression. So basically in confusion matrix, we find out the actual non-events that were predicted as non-events and actual events that were predicted as non-events. Similarly, we also calculate the actual non-events which were predicted as events and actual events which were predicted as events. Finally, what we do is we calculate the total correct number of predictions, that is actual events that were predicted as events and actual non-events which were predicted as non-events, and divide them by total number of predictions. That gives us the percentage amount of how many correct predictions were made, and we can also measure the false positives in this case and divide them by the total number of predictions. This is an important measure of direct marketing in terms of the cost of around mailing. As an analytic trick, it is often helpful to determine if the dependent variable has any abnormal observations. Remember the z-score. This is a fast and simple way to check if an observation is out of bounds. The z-score calculated is by observation minus mean by standard deviation. Let's say the mean of revenue is $358 and the standard deviation of revenue is $569. So if you run this calculation for all observations on revenue, you will see that 2100 minus 358 by 569 is close to 3. This means that the observation is greater than 3 standard deviations from the mean, a very non-normal observation. It is common to add a new variable, call it positive outlier, and it will take the value 0 as long as z-score on sales is less than 3. Then it takes the value of 1 if z-score is greater than 3. Use this new variable as another independent variable to help the account for outliers. Lift charts. This is a simple analytic device to ascertain general fit as well as targeting aid in terms of how deep to mail. The general procedure is to run the model and output the probability to respond. Sort the database by probability to respond and divide into 10 equal buckets. Then count the number of actual responders in each decile. If the model is a good one, there will be a lot more responders in the upper deciles and a lot fewer responders in the lower deciles. As an example, say the average response rate is 5%. We have 10,000 total observations. Each decile has 1,000 customers in it. Some of them have responded and some of them have not. Overall, there are 500 responders. So, randomly we would expect on average 50 in each decile. Instead, because the model works, say there are 250 in decile 1, and it decreases until the bottom decile has only one responder in it. The lift is defined as the number of responders in each decile divided by the average number of responders. In decile 1, it means 250 by 50, that is 500%. This shows us that the first decile has a lift of 5x, that is, there are 5 times more responders than the average. It also says that those in the top decile who did not respond are very good targets, since again they all look alike. This is an indication the model can discriminate the responders from the non-responders. Note that in each decile there are 1,000 customers. 250 already responded in decile 1, All of the customers in decile 1 have a high probability of top 10% responding. There are 750 more potential targets in decile 1 that have not responded. This is the place to focus targeting, and this is why it is called clone modeling. To briefly address the database marketing question, how deep do I mail? Let's look at the lift chart above. This is the accumulation of actual responders compared to expected responders, depending on the budget, etc. The lift chart helps to target. Most database marketers will mail as far as any decile outresponds the average, that is, until the lift is less than 100. Another way of saying this is to mail until the maximum distance between the curves is achieved. However, on a practical matter, most direct marketers have a set budget and can only afford to mail so deep regardless of the statistical performance of the model. Thus, most of the attention is on the first one or two deciles. Now we will discuss about collinearity. Another very common issue that must be dealt with in regression modeling is collinearity. Collinearity is defined as one or more independent variables that are more correlated with each other than either of them is with a dependent variable. That is, if there are two, say, independent variables in the model, damaging collinearity is if x1 and x2 are more correlated than x1 and y, or x2 and y. Mathematically, probability of correlation of x1, x2 is greater than probability of yx1 or probability of yx2. The consequence of collinearity is that where the parameters estimates of each independent variable remain unbiased, the standard errors are too wide. This means when significance testing is calculated, parameter estimates or standard error of the estimate for a t-ratio, these variables tend to show less significance than they really have. This is because the standard error is too large. Collinearity can also switch signs which return nonsensical results. Thus, collinearity must be tested and dealt with. A quick note on overly simplistic diagnostics I have seen in practice follows. It's possible to run a correlation matrix on the variables and obtain the simple Pearson correlation coefficient for each pair. This does not check for damaging collinearity. This is a check for simple linear correlation. I have seen analysts just run the matrix and drop an independent variable just because the correlation of it and another independent variable is, say, greater than 80%. Why did they get 80%? This is an arbitrary and beneath anyone calling themselves analytic. Okay, off the soapbox. The above testing is irksome because real testing is relatively easy. VIF is the most common. Run proc regress and include VIF as an option. VIF is the variance inflation factor. Basically, it regresses each independent variable on all other independent variables and displays a matrix. This metric is 1 by 1 minus r square. If this metric is greater than 10, then as a rule of thumb, some variables is too collinear to ignore. That is, if there are three independent variables in the model x1, x2 and x3, VIF will regress x1 equal to function of x2 and x3 and show r square, then x2 as function of x1 and x3 and show r square, and last x3 as function of x1 and x2 and show r square. Note that we are not really testing for collinearity because there will nearly always be some collinearity. We are testing for collinearity bad enough to cause a problem. The recommended approach is to include variables that make theoretic sense. If VIF indicates a variable is causing a problem, but there is a strong reason for that variable to be included, one of the other variables should be examined instead. It is important to note that dropping a variable is not the first course of action. Simply dropping a variable is arbitrary and very simplistic analytics. That is A stronger, more defendable model results from a strategic understanding of the data generating process, not based on statistical diagnostics. The science of modeling would emphasize diagnostic. The art of modeling would emphasize balance and business impact. Did I mention sometimes in a practical business environment, bad statistics are allowed balance on running a business? Depending on the issues and data, etc., other possible solutions exist. Putting all the independent variables in a factor matrix would keep the variables variance intact, but the factors are by definition orthogonal. Another technique is called ridge regression, typically using stain estimates, and requires special software and expertise to use. In general, it trades collinearity for bias in the parameter estimates. Again, the balance is in knowing the coefficients are now biased, but a drastic reduction in collinearity results. Is it worth it? Sorry, but the answer is it depends. While VIF is helpful, the condition index has become the state of art in collinearity diagnostics. The maths behind it is fascinating, but many textbooks will illuminate that. We'll focus on an example. The approach, without getting too mathematical, is to calculate the condition index of each variable. The condition index is the square root of largest eigenvalue divided by each variable's eigenvalue. An eigenvalue is the variance of each principal component when used in correlation matrix. Eigenvalues add up to the number of variables, including the intercept. This is a powerful diagnostic because a set of eigenvalues of relatively equal magnitude indicates that there is little collinearity. A small number of large eigenvalues indicates that a small number of component variables describe most of the variability of the variables. A zero eigenvalue implies perfect collinearity, and this is important. Very small eigenvalues means there is severe collinearity. Again, an eigenvalue near zero indicates collinearity. As a rule of thumb, the condition index is greater than 30 indicates severe collinearity. Common outputs along with a VIF and condition index are the proportions of variance. This proportion of variance shows the percentage of the variance of the coefficient associated with each eigenvalue. A high proportion of variance reveals a strong association with the eigenvalue. Let's talk about table 4.6. First look at condition index when we discuss the problem later. Now a brief procedural note. And probably most of the analytic techniques we will talk about, certain assumptions are built in. That is, regression has many assumptions about linearity, normality, etc. While for OLS I mentioned one assumption, especially for time series data, was no serial correlation. This same assumption is applied to logistic regression as well. Most regression techniques used most of these assumptions. So while in Logit I showed how to test and correct for collinearity, the same test needs to be applied in OLS as well. It just happened to come up during our discussion of logistic regression. This means that in reality, for every regression technique used, every assumption should be checked and every violation of assumption should be tested for and corrected if possible. This goes for OLS, Logit, and anything else. Variable diagnostics. As in all regression, a significance test is performed on the independent variables, but because Logit is nonlinear, the t-test becomes the world test. The p-value still needs to be less than 0.05. Pseudo R-square. Logistic regression does not have an R-square statistics. This freaks a lot of people out, but that's why I showed the confusion matrix. which is a measure of goodness of fit. Remember, R square is the shared variance between the actual dependent variable and the predicted dependent variable. The more variance these two share, the closer the predicted and actual dependent variables are. Remember, OLS outputs an estimated dependent variable. Logistic regression does not output an estimated dependent variable. The actual dependent variable is 0 or 1. The logit is the natural log of the event divided by 1 minus event, so there can be no estimated dependent variable. If you have to have some measure of goodness of fit, I would suggest using the log likelihood on the covariate and intercept. Scoring the database with probability formula. Typically after logistic regression is run, especially in a database marketing process, a model has to be applied to score the database. SAS now has proc score, but I want you to be able to do it yourself and to understand what's happening. It's old-fashioned, but you will know more. Now let's move on to market basket. In economics, a market basket is a fixed collection of items that consumers buy. This is used for metrics like CPI, inflation, etc. In marketing, a market basket is any two or more items brought together. Market basket analysis is used, especially in retail, to bundle and offer promotions and gain insight in shopping purchasing patterns. Market basket analysis does not by itself describe how the analysis is done. That is, there is no associated technique with those words. How is it usually done? There are three general uses of data: descriptive, predictive, and prescriptive. Descriptive is about the past. Predictive uses statistical analysis to calculate and change on an output variable, example sales, given a change in input variable say price. And prescriptive is a system that tries to optimize some metric, typically profit, etc. Descriptive data means frequencies, KPIs, etc. is necessary, but not usually sufficient step. Always get to at least the predictive step as soon as possible. Note that predictive here does not necessarily mean forecasted into future. Structural analysis uses model to simulate the market and estimate what causes what to happen. That is, using regression, change in price shows what is the estimated change in sales. Market basket analysis often uses descriptive techniques. Sometimes it is just a report of what percent of items are purchased together. Affinity analysis, a slight step above, is mathematical, not statistical. Affinity analysis simply calculates the percent of time combinations of products are purchased together. Obviously, there is no probability involved. It is concerned with the rate of products purchased together and not with the distribution around that association. It is very common and very useful but not predictive, therefore not so actionable. Logistic regression. Let's talk about logistic regression. This is an ancient and well-known statistical technique, probably the analytic pillar upon which database marketing has been built. It is similar to ordinary regression in that there is a dependent variable that depends on one or more independent variables. The use of logistic regression in terms of market basket becomes obvious when it's understood that the predicted dependent variable is a probability. The formula to estimate probability from logistic regression is Pi is equal to 1 by 1 plus e to the power minus z, where z is equal to alpha plus beta xi. This means that the independent variables can be products purchased in a market basket to predict likelihood to purchase another product as a dependent variable. Note that there is not an issue of causality here, that is, presupposing that one independent product causes the purchase of the dependent product, only that they are associated together. The above means to specifically take each major category of product, focus driven by strategy, and running a separate model for each, putting in all significant other products as independent variables. For example, say we have only three products X, Y, and Z. The idea is to design three models and test significance of each, meaning using logistic regression. X as function of Y and Z, Y as function of X and Z as function of X and Y. Of course, other variables can go into the model as appropriate, but the interest is whether or not the independent product variables are significant in predicting the probability of purchasing the dependent product variable. Of course, after significance is achieved, the insights generated are around the sign of the independent variable. That is, does the independent product increases or decreases the probability of purchasing the dependent product. An example would be, say we are analyzing a retail store with categories of product like consumer electronics, women's accessories, newborn and infant items, etc. Thus, using logistic regression, a series of models should be run. That is, consumer electronics is a function of women accessories, jewelry, watches, furniture, entertainment, etc. This means that independent variables are binary, coded as 1 if the customer bought that category and as 0 if not. Note that other independent variables can be included in the model if significant. This would often be seasonality, consumer confidence, promotion scent, etc. To interpret the model, if a customer bought consumer electronics, that increases the probability of buying home decor by 29%. If a customer bought newborn infant items, that decreases the probability of buying home decor by 37%, and so on. That is, offering say home decor and furniture together make great sense, but offering home decor and newborn infant items does not make sense.